Good day and welcome back to part 4 of our discussion of double integrals over general regions. During a typical semester where we are meeting, on campus face to face, this is really where I would be beginning the second part or second day of our discussion, and I think it's a great opportunity for us to just do a bit of review. In terms of double integrals, what are some of the big things that we've encountered? First of all, what is the interpretation? A double integral over a region D, which could be a rectangular region or a general region, i.e. non-rectangular, is interpreted as a quote-unquote volume, i.e. I really mean a net difference of volumes, enclosed by the graph of that function, the surface z equals f, and the z equals 0 plane relative to this region D. And the really important part for us is being able to take a double integral in its more general form and set it up as an iterated integral. And let's do this for the three big scenarios we see below. For the first region we have sketched, this is the absolute most ideal scenario we will ever encounter, a rectangle. And when we're setting up a double integral over a rectangle, we have a lot of freedom. We can, for example, decide the order of integration that we would like to use, and if the function we are integrating separates into a function of x times a function of y, we can even break it up into a product of single integrals. In this case, I'll just go ahead and simply put x on the inside, y on the outside, so x from a to b, y from c to d. But of course you could change that direction if you prefer, and remember that we evaluate these integrals from the inside. For this second example of a generic region, D, we see that it's varying or bounded nicely between numbers in the x direction and functions in this vertical y direction. And what this is an indication of is how we should set up our limits of integration. We want to make sure that on the outside we have numbers. And we see that the x values are varying very nicely from a to b, our outer limits of integration. But we also need to know for a generic x value between a and b, how do those corresponding y values vary? And they will vary along these vertical line segments where they go from the smaller function, y equals g1, our inside limit, to y equals g2, our upper limit. And this was one of those so-called type 1 regions. In terms of the third example that we have pictured, note in this case we see that the region D is bounded nicely in the y direction between numbers c and d, and in that horizontal x direction it's bounded by nice continuous functions h1 and h2. So that's an indication that when we set up our limits of integration and we want numbers on the outside, we should go dy on the outside, dx on the inside. In terms of y values on the outside, we're varying from c to d. And on the inside, we can note for a generic y value between c and d, how do those corresponding x values vary? And they vary along horizontal line segments, going from a lower value h1 of y to an upper function h2 of y. And that gives the lower and upper limits of integration respectively. And the thought process of going from a region to this iterated integral is one of the most important concepts in this section. So with that in mind, let's go ahead and move on to this example, given some room here. So let's evaluate the double integral over the region D, where D is a region enclosed by x equals 0. Okay, so we can draw this. X equals 0 would correspond to the y-axis, and x equals the square root of 1 minus y squared. So we might have to think a moment to sketch this, but let's just do a little bit of manipulation. The reason this is looking difficult to deal with is potentially because of the square root. So if we square both sides, x squared is 1 minus y squared, we would end up with x squared plus y squared equals 1. That is a circle of radius 1 centered at the origin. But note it's not the entire circle because our x values are restricted to being non-negative. That is bigger than or equal to 0 because they're the square root. So it would indicate the right half of a circle of radius 1 centered at the origin. So roughly speaking, we have -1 and 1 in the y direction, 1 in the x direction, and this is the graph of x equals the square root of 1 minus y squared. And the region enclosed between this half a circle and the y-axis is what we call D above. Now, just to make kind of a side note that may be of interest, we will very frequently encounter circular regions of integration. So it's important to be able to quickly and efficiently recognize when we have a semicircle, that is one of the halves of a circle. So for example, if you wanted to solve for the upper or lower half, we could rewrite this equation as y equals plus or minus the square root of r squared minus x squared. And the positive portion of that would be the top half of the circle. And this would be a circle of radius r centered at the origin. Whereas the negative would correspond to the bottom half. Y is minus the square root of r squared minus x squared. Similarly, if you wanted to picture the left and the right half of this circle, you could instead solve for x. And if you start with x squared plus y squared equals r squared, and you isolate x, you would end up with plus or minus the square root of r squared minus x squared. The positive square root would correspond to the right half of this circle, and the negative square root would correspond to the left half of the circle. So just note, circular regions of integration come up frequently, and based upon equations such as the one given here, it is definitely beneficial to be able to quickly and efficiently recognize and sketch these curves. With that being stated, let's go ahead and evaluate this double integral of interest. We have the double integral over the region D of x, y squared. And I would like to note that we can really set this up to be either a type 1 or a type 2 region, depending upon your preference. But simply in terms of this equation already being given to us, it's probably easiest just to think of this as one of these so-called type 2 regions. So if we want to think about this from the outside in to set up our limits of integration, we can see that the y values are varying between -1 and 1, and the x values vary from x equals 0 until we hit this other x equals curve. So the indication is that we should have y on the outside, x on the inside. So y would be going from -1 to 1, and the x values would vary accordingly. For any y value between -1 and 1, your x values vary from this lower curve, x equals 0, to this upper curve given your upper limit of integration. So that would be from 0 up to the square root of 1 minus y squared. And let me note that just on a very intuitive level, this setup certainly has the right feel to it. We see that we have constants as our outside limits of integration, and on the inside, when we are integrating with respect to x, the variable we see in our limits of integration corresponds to that other or outside variable of integration. And before evaluating, let me make an observation. We have a function of x times a function of y squared. That is to say, our integrand separates over multiplication. So can I split this up into two single integrals? And the answer is no. And the reason it's no is because we are not integrating over a rectangle. The only time we can split it up is when we are over a rectangle, which we certainly do not have in this case. So our choice is to really just work from the inside out. So taking care of that inside integral, the antiderivative of xy squared with respect to x would be 1/2 x squared y squared. We're evaluating from x equals 0 to x equals the square root of 1 minus y squared. Note it works out rather conveniently in the sense that we have 1/2 as a constant that pulls out front. When you square a square root, it goes away, and what you get when you plug in 0 is simply 0. So creating just a little bit more space, we have the 1/2, the integral from minus 1 to 1, y squared minus y to the 4th. And this is the ideal scenario when it comes to evaluating antiderivatives. We simply have powers of our variable y. So that would be 1/3 y cubed minus 1/5 y to the 5th from minus 1 to 1. So we substitute in a 1, we put a minus sign, we substitute in a minus 1. And I'm not going to bore you with the arithmetic here, but if you do that and you even wanted to simplify this, you will end up with 2/15. But let me just note once again, you don't need to simplify this all the way down. You could simply plug in 1, minus sign, substitute in minus 1, and call that good. That completes the material for this video, but we'll continue on in the next few videos looking at some of the subtleties and the different ways we can ask the questions. So stay tuned and take care.